Okay, cool. Well, let's get into it. So as we saw in the videos leading up to this class, we are beginning to look at the derivative, and the derivative was really just defined in terms of a limit, but not a limit of our function f of x. Instead, it was the limit of this difference quotient, right? So it was the, oh, there we go. It was the limit of this expression here, right? So if our p-value is fixed, then that expression is a function of x, and it's not defined at p, right? The big expression in the parentheses is not defined at p, but it is defined potentially for nearby points to p, so nearby x values. And so because of that, it made sense to take a limit as x approached p, and this would be the limit of a function as we approached this point in question. So the idea was that if this limit existed, then, and it equaled some value L, then we would say that the function was differentiable at P, and the limit, which we might have previously called L, right? So maybe back in our function, in our class on limits, function limits, we might have called that the limit L. Instead, we'll give that a special name in this case. We'll call it f prime at P. Right, and so in the video, we discussed these different limits, or we discussed limits of this form. We said that it was equivalent to this form. This is often the form that we use in Calculus 1 especially, because in this form, I should say, we're able to often algebraically manipulate these limits. So you might remember way, way back when you were trying to rigorously prove that the derivative of x squared existed, right? You might use an expression like this, so it would become p plus h squared minus p squared, and you would algebraically manipulate that. So in Calc 1, we often use this example, or we often use this notation. In truth, we can really use either of these notations, and there will be times when you might want to use one, times when you might want to use the other. Today in class, we'll primarily use this top notation. So we had all of that as far as these derivative definitions went. And then we were able to prove a couple of things in the videos, including lemma 10.7, which says that if a function is differentiable, then it is continuous. And we were able to prove this, the sum rule, right? And so here we're starting to get into these sort of well-known facts about derivatives. The sum rule said that if you have the sum of two functions, f plus g, and you wanted to take the derivative of that, then you would calculate that by taking the derivative of f and taking the derivative of g and adding those two together, right? And so that was what we saw in Theorem 10.8. Yeah, I don't think there's too much to say about that, except maybe to reiterate something that we saw in the video, just that we can, or we should remember that this is really denoting a limit. So when I say f plus g prime at p, what I'm really saying is that the limit as x approaches p of the expression, right? And then it would be, we've got to get the parentheses right here, f plus g of x minus f plus g at p. Didn't quite give myself enough space there. F plus g of x minus f plus g of p all over x minus p, right? This is what is represented when I use this notation here. So when I said this expression equals this expression, what I really was saying is I can compute this limit. The limit is well defined and exists. And it turns out that it is equal to whatever this limit is plus whatever this limit is, right? And we saw in the video, I don't necessarily need to rehash every detail because you've already seen it, but just to point out, this was the same thing as we sort of split this up. Limit as x goes to p. We had f of x and then plus g of x, and then minus f of p minus g of p. So we sort of distributed everything over here. right? We sort of regrouped everything. This was all over the common denominator x minus p. So we could write it if we chose like this, just splitting it across that common denominator. And then in fact, the actual process of proving this meant that we had to sort of take this piece and break it up across the limit. So it became the limit of this plus the limit of this. And we could do that by referring to our theory about algebraic, or the algebraic limit theorems for functions, right? So the limit of one function plus another function. So indeed, we could see that that was equal to the limit of the first piece plus the limit of the second piece. And by definition, the limit of the first piece, that was equal to f prime. The limit of the second piece was equal to g prime. So this is a really, really common sort of strategy when we're dealing with these kinds of derivative expressions, sort of like figure out exactly what is really being said in terms of limits and use some of our previous work about limit manipulations to try to, break this down, split it up in the appropriate way, and recombine it up here. So I think that was the final video that we saw. Any questions about any of that?
I think we're good.
Cool. Awesome. Love it. So in that case, let's jump into so this was the question, I would say, so this was the question that you all were asked to look at in your preliminary work today. I think it might be slightly rephrased here, but we had a function f that was differentiable on an open interval a to b. We had some point in the middle that satisfied f prime of c equals 0. And then we had to prove this statement about every delta. For every delta, some small number, we could find points in the delta neighborhood that satisfied this set of inequalities. So the big idea here, I think, was really parsing out exactly what this meant. The fact that, this one fact that we knew, which was that f prime of c was equal to 0. And so as you explored this, right, so we could have our open interval a to b, a to b. We could have a c value somewhere in the middle. And the one thing that we knew was that f prime of c was less than 0. And again, what that means is we know that the limit as x goes to c of f of x minus f of c all over x minus c, we knew that that was equal to some number f prime of c that was less than 0. Right? And so to approach this, we really have to parse out exactly what this statement means. And so as you did this, you probably saw that this meant for all epsilon. So we know for all epsilon, there exists a delta such that if absolute value of x minus c is less than delta, then this expression, the entire difference quotient, f of x minus f of c over x minus c, that entire expression right, minus f prime of c would be less than 0, would be less than epsilon. Okay, so maybe I should say, so this was like our way of saying that that limit was equal to some f prime of c, and that was definitely less than 0. But sort of the key observation that we want to make here is that if this is true, right, so if f of x minus f of c over x minus c minus f of c is less than epsilon, then by choosing an appropriately small epsilon, we should be able to make f of x minus f of c over x minus c negative as well, right? So this number is negative. These two expressions are reasonably close to each other, right? They're within an epsilon's distance. So if this is negative and this is even smaller, then this piece will also have to be negative. And so one observation that we can make is if we let epsilon be really tiny, right? And in this case, we could say that epsilon is, let's say, less than or equal to f prime of c over 2, sort of a nice trick to use. So if it's less than f prime of c over 2, then the quantity f of x minus f of c over x minus c is negative. For x values in the delta neighborhood of c. So for x minus c less than delta. Right, so the intuition there, I think, the intuition there is that if I have a number line, just sort of draw it over here, if I have this number line and if I take, let's say this is 0, and if I have f prime of c is less than 0, right? So if f prime of c is less than 0, then I can take this quantity, right? If I let epsilon be equal to some number less than or equal to f prime of c over 2, well, I can measure this distance, right? Cut it in half. So this distance here, this is going to be our f prime of c over 2 distance. Right? And so the corresponding epsilon neighborhood around f prime of c is all going to stay negative. So f prime of c is negative, and I've made my epsilon small enough that that entire little epsilon neighborhood is also negative. And so because of that, right, that means that this quantity will have to be somewhere in that epsilon neighborhood. It'll have to be within that epsilon distance of f prime of c, so it will also be negative for x minus c values in the corresponding delta. So for x values in that delta, right, maybe let's jump back to our first picture up here, right? And let's say that that corresponding delta is maybe this range, right? So if our corresponding delta is this range, then we can think about x values that are in that range. And now we can try to set up the appropriate numbers here. So we're looking for two values, x and y, that are within this delta neighborhood. And we want to choose x less than c less than y. So we could point to just sort of 2 points arbitrarily. Let's say that's my x and that's my y. And because they're inside this delta neighborhood, we know that for those two numbers, this holds true, right? So this quantity is negative. And so we can explicitly compute, let's do it in the example of y, or let's do it in the example of x first. So if that's our x value, then we know for x, we know that the quantity f of x minus f of c over x minus c is negative. That's true just because it's x is inside the delta neighborhood. But we also know that the quantity x minus c, right? Well, x is less than c. We sort of positioned it to the left of c, so x is less than c. And so x minus c is also negative. So for that chosen x value, the fraction, that difference quotient is negative, but also x minus c is negative. And so it must be the case, so we must have f of x minus f of c is positive. Right? And so therefore, we've got f of x is bigger than f of c. All right, so this is I think, maybe slightly technical, but really precise argument to say that if we have our derivative is negative at a given point, then if I zoom in close enough to that point, right, I find an appropriate epsilon, and I zoom in into this really close delta neighborhood near that point, I can find x values just a little bit to the left of, in this case, c, x values just a little bit to the left of c, for which f of x is bigger than f of c. And we can do a similar argument for y as well. So if we've got our f of y minus f of c over y minus c, that should be negative. But y minus c in that case would be positive. And so it must be the case then that f of c is bigger than f of y. Right? And so the picture, the sort of intuitive picture that we have, is that for such a function, right, let's say we have a differentiable function and we've got, this is our c value, then if our function is negative there, or I'm sorry, if our function's derivative is negative there, then we expect our function to be decreasing. And as it decreases, we expect to be able to find x values and y values on either side, such that f of x is just a little bit taller than f of c is just a little bit taller than f of y. And so we have this nice technical argument that describes the sort of picture that we have in our head as well. So I think that's sort of, again, a slightly technical argument for a nice, that helps describe this nice intuitive picture that we have. And the technical element of it comes from sort of analyzing this quantity, this time in terms of epsilons and deltas, and figuring out how to parse that out. Okay. Pause for 1 second. Any questions, comments, concerns? Were people sort of thinking in this term or these terms? Were they thinking sort of more in terms of this? Yeah, I think this was a slightly technical argument, so I wanted to you know, prime you to think about it a little bit and then talk through it at the start of class today. Any questions? Something in the chat. Thumbs up, the picture helps. Love it. Yes, 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 yes. Yeah, thanks. I do think the picture helps a lot in this case. All right. Okay, cool. Let's see, what else can we say? Let's move on to the next thing. So our big thrust today, and maybe I was sort of, yeah, our big thrust today is to try to prove some of our favorite rules from Calc 1. Specifically, we're gonna try to prove the product rule. We'll skip the quotient rule, but if we have time, we will also prove the chain rule. So our big goals are the product rule, number 1, and then the chain rule, number 2. Okay, so let's talk through the product rule first. So the product rule, as we know, is that if we take oh, look at this, I think, it looks like I tried to copy and paste from somewhere else and I included something extra. Sorry about that, let me erase that. The product rule says that if you have two differentiable functions, f and g, and they're differentiable at a point p, then we can calculate the derivative of the function f times g, the product of the two, right? And we know that when we have f times g and we take its derivative, we get the derivative of the first function times the second, plus the derivative of the second function times the first. Right? We love the product rule. We use the product rule all the time, but possibly before today, we haven't seen a really rigorous, believable proof that the product rule holds true. So our goal for today is to try to prove rigorously that the product rule holds true. And to do that, we are again going to have to think about our rules of limits and really remember what this expression is saying, right? So this expression, f times g prime of p, this is really representing a limit as x goes to p of f times g of x minus f times g of p all over x minus p. Okay, our goal is to show that that limit rigorously exists and can be computed if we happen to know that f and g are differentiable at p, meaning we know that f prime of p, that limit exists, right? So the limit as x goes to p of f of x minus f of p over x minus p. So we know that that exists, and we know that g is differentiable, so we know that g prime of p exists, and so that's the limit as x goes to p of g of x minus g of p over x minus p. So we know that that both of those individual limits exist, and the question is, can we rigorously show that this limit exists? So it turns out we can, but we have to be very clever about it. We are going to make a really clever algebra move to begin manipulating this and ultimately breaking it up. So maybe first of all, just to rewrite this a little bit, the function f times g, right? When I say fg of x, what I mean is the output that I get when I take f of x times g of x. So rewriting this, we're going to get, I'm just rewriting explicitly what this means. So f times g of x is really the function f of x times g of x. And then we've also got a minus fg of p, so that's going to be minus f of p times g of p. I'm giving myself a lot of room here. And then all of that is over the expression x minus p. Now, to keep going forward, we want to do a really, really clever addition in the middle. We want to add 0, but in a really clever way. So we are going to add the quantity. So I'll do plus. I'm going to add f of x times g of p minus f of x times g of p. Right, so notice, taken together, the thing that I've added is really just equal to 0, and I haven't really changed my limit at all. So the top line is really equal to the bottom line, right? These two things are equal to each other. But what this is going to allow me to do is break up this limit into two different pieces. And I'm going to do that as follows. I'm going to take this first piece, and I'm going to take this third piece, right? And those will be my green pieces. And so taken together, I'm going to write this as f of x g of x minus f of x g of p all over x minus p. That's my green piece. And then for my, let's say, orange piece, I'm going to take the second and fourth pieces, right? And so that's going to give us the second and fourth pieces. That's going to give me an f of x g of p minus f of p, g of p, all over x minus p. Okay, and what we really have at the moment, just by rewriting, I have the limit as x goes to p of all of this stuff taken together, right, with addition here. So it's the limit of that first piece plus the second piece, and I'm just doing some clever rearranging, rewriting, and then sort of clumping. Now, we can use our properties of limits, right? Specifically our function limit laws, or our algebra of limits. So the algebra of limits says that the limit of this whole thing is going to equal the limit of the first piece plus the limit of the second piece, provided that this limit exists and that this limit exists. So as long as each of those individual limits exist, then so should the limit of this whole thing. And that's by our material back in, I think, chapter 6. That's our algebra of limits. So, well, we're going to get that this is equal to this line. And by the algebra of limits, I'm just going to save a little space, do a little sleight of hand. This is just equal to the limit of the first piece plus the limit of the second piece as x goes to p for both of them. Right, so that was true now by our algebra of limits. Okay, and this is great. So at this point, I just have to examine each of these individual limits, and we can begin to see the structure in which these two limits will fall into these two camps right here. Let's start with our green. Okay, so let's start with our green one. So the limit as x goes to p of, now let's see, this was f of x times g of x minus f of x times g of p all over x minus p. Well, our limit rules, again, come into play. We see that there is an f of x in each of these terms in the numerator. And so each of those terms in the numerator can be factored, right? So we can factor out this f of x, and we get g of x minus g of p over x minus p. But we can pull that f of x outside of the limit. We want to think a little bit about this, but again, our rules of limits say that if I have oh no, wait, that's not quite what I mean to say. I apologize. I don't want to pull this out, but I want to evaluate the limit as x goes to p of this piece separately from the limit as x goes to p of this piece. So let me write that as the limit of f of x times the limit of this fraction. Now, while I'm writing this, why can we do this? How do we know that we're allowed to break this up into the limit of the two pieces?
Algebra of limits.
Yeah, it's sort of our go-to trick, this proof, isn't it? Exactly, Joel. Yes, the algebra of limits says that I can take the limit of the one piece times the other and turn it into the limit of the first piece times the limit of the second piece. That's exactly right. And now when we evaluate this first piece is going to be just, well, it's just the limit as x goes to p of f of x. That's just going to be f of p times, well, this second piece, we knew that the function g was differentiable and that g prime of p could be expressed as this limit. So we know that this limit exists, and by definition, it will be g prime of p. So we get f times g prime. Okay, and that is our green piece of the puzzle. I'm going to box that off in green. And I won't go through in all of the same gory detail the orange argument, but the orange argument will be basically the same. we'll end up getting, oh, that's still green. We'll end up getting that the argument in the orange box, right, or the limit there, is just going to boil down to, we'll have this g of p, that's the one we'll be able to pull outside the limit. So it'll be g of p times the limit as x goes to p of f of x minus f of p all over x minus p. And so that whole thing will just simplify down to g of p times f prime of p. And we've actually completely, totally done it. Look at this. So what we have now is our original limit. Let's walk through the entire argument. The original limit could be rewritten, and we could add and subtract 0 in a clever way. At this point, I could group things appropriately into these two halves. And by the algebra of limits, I could break that into the limit of this first piece plus the limit of this second piece, assuming that both of those existed. So I have to sort of put a big asterisk there and say, let's make sure that these both exist. That will justify the fact that I can split them up. Then we jump into our two boxes, right? And in our green box, boop, in our green box, we're able to keep using the algebra of limits to simplify and simplify until we get this expression, which we know exists because we knew that g was differentiable. For the orange, we get a similar box. We can break everything down, and we see that that exists because we knew that f was differentiable. So therefore, and I'll jump back to black ink to finish it off, all of this simplifies down to the, I'll write the orange piece first, because that's how we typically do it, f prime times g, plus the green piece, which turned out to be nothing more than f times g prime. And we are done. Awesome. Awesome, awesome. Product rule proven. Sorry about that. Any questions, comments, concerns, thoughts about this argument? Okay, cool. Yeah, kind of a fun argument. We're not going to spend time in class proving the quotient rule, but the quotient rule, I will say, is proven very similarly, right? In which you set up the initial quotient, you have to add or subtract 0 in some interesting way, and you have to use some clever algebra maneuvers. So yeah, so we won't do it in this class, but it is very, very similar. One that we want to spend a little bit of time with, though, is the chain rule. And so we're going to talk about the chain rule here. The chain rule was always the most complicated of our rules back when we were learning it in calculus. And it turns out it's the most complicated of the rules here as we try to prove it in real analysis. Even the statement is more challenging. So let's talk through this statement briefly. So we have the f and g are two functions. We have f is a function with a domain of a. G is a function with a domain of b. And we're sort of assuming, or we're specifying at the beginning, that the image of a is a subset of b. What that means is, right, so g is a, right, g is a function that has b as a set, and it's mapping it into the real numbers, right? So g is a function that maps b, the set b, into the real numbers, while f is a function that maps a into the real numbers. All we're specifying here is that f of a, the image of a, is a subset of b. So our function f maps things from a into b, and that means that we could therefore create the composition g of f, in which we take some number in a, map it using f into here, and then plug that into G to get out here. So we get this composition of functions, right, which I'll draw in purple. Boop. We get the composition of functions that goes from one to the other, and that's just going to be G of F. And that has as its domain at least the set A into the real numbers. So we're defining these two functions. We're assuming that point P is a point in A. I realize this should actually say P is an element of A. I apologize. So P is some element of A. Let's call it P. Just draw it right there. So P is some element of A. And we're assuming that F is differentiable at P. So F, we can compute the derivative of F at the point P. And G is differentiable at F of P, right? So P maps into here, and maybe this is the point F of P. So the function F is differentiable at this point in its domain, and G is differentiable at this point in its domain. So with all of that, right, a lot of specifications there. With all of that said, we can conclude that G of F, the composition, is differentiable at P, and that G of F prime is equal to G prime of F times F prime, right? So the chain rule that we know and love, G prime of F of P times F prime of P. Cool. Okay, so we're going to spend a chunk of time for the rest of class trying to prove the chain rule. First, I'm going to just write it in a more simpler notation. So I'm just going to say, boop, with F and G defined suitably, right? And suitably, of course, is a loaded word. But when I say suitably, this is really what I mean right here, right? Defined in the appropriate manner so that you can create the composition and have the composition be differentiable. So with that, with F and G defined suitably, we're saying that G of F is differentiable and G of F prime is equal to this quantity here. Okay, so first, let's keep in mind what we're trying to prove. We need to take this expression, show that it exists and that it actually equals the expression on the right-hand side. And so the expression here, G of F prime, that's really going to be a limit quantity, right? So G of F prime, it's going to be the limit as x goes to P of the quantity, and let's get this right. So it's going to be G of F of x minus G of F of P, all divided by x minus P. That's what we can, how we can formally write this out. So we are trying to show that this limit exists and it actually equals this quantity right here. Now, let's take a look at this. I want to, maybe I'll say, this is more challenging than it first looks. Or rather, I think at first it looks really challenging. Then we think we see it. And then we realize it's actually more challenging than we realized. So first, this looks challenging. Then we notice that we might be able to do something clever like we did in the sum rule. We might be able to not add 0, but instead cleverly multiply by 1. Right? If we can multiply the top and bottom of this by the same thing, it feels like we shouldn't be changing anything. Right? So if I multiply by something here, and those are the same, then I'm not really changing the limit. And the move that we think is so clever, and it's very clever, and it's almost right, but it's not quite, is to multiply by f of x minus f of p over f of x minus f of p. So this feels like it should be right, and it's so seductive almost that I would call this a seductive false proof. And I want to walk through this false proof because it's worth sort of identifying why it's false. But first, let's see how right it looks, how good it looks. So this is the false proof. The quantity on the left here, right, this was just our g of f prime at p. That was the formal definition. And what we think we've done, right, is we think we've multiplied top and bottom by f of x minus f of p over f of x minus f of p. Now, if we try to do that, we can rewrite it in this way, right? So notice over here, I've rewritten it. I've moved one of the f of x minus f of p's over here, so that now it's g of f of x minus g of f of p over f of x minus f of p, and then times f of x minus f of p over x minus p, right? So I multiplied by 1, and then I shifted what was in the numerator over what, and now I can begin attacking these separately. So by the algebra of limits, we like to think we can break these up, right, into the limit of the first times the limit of the second. The limit of the second, right, maybe I'll just sort of notice this right away. The limit of the second piece is nothing more than f prime of p. And so that's pretty awesome. And for the piece on the right, I might be able to rewrite this so that it's not x going to p, but it's some quantity going to f of p, right? So notice what we do here on the left. What we do is I sort of blur my eyes a little bit and I say, let me call the entire expression f of x. Let me call that z. So I get g of z minus g of f of p over z minus f of p. And maybe I no longer think about x going to p, but I think about this quantity z going to f of p. And if I do that, right, and I get down here, then this is nothing more than the derivative of the function g evaluated at the point f of p. Right, I'm using a z instead of an x, but you'll notice that that has the exact same structure as our derivative from before. And then we've gone and we've proven that this limit is equal to g prime of f of p times f prime of p. Oh man. See, so doesn't that look like so good? That looks like it should be a complete and correct proof. And it gets us exactly what we want. It turns out though that this is actually not really valid. Almost every step is valid, but there's something weird happening. There's something weird happening in this piece right here as I begin to blur my eyes and just plug in the number z instead of the number f of p, or instead of x. And the trouble actually, maybe I'll say this out loud, or I'll try to find a nice way to shorthand it. This almost works, right? It almost works, except if f of x is equal to f of p near x equals p. Right? The trouble is going to come from the possibility that our function f looks something like this. Right? Maybe this is my function f, maybe this is the point p. If my function f becomes really flat for a while and then keeps going, right? If nearby x values, like say this one, have f of x equal to f of p, then this move isn't valid. In fact, it's a little iffy that I can actually divide by f of x minus f of p to begin with, right? Or in other words, if there's a long stretch in my function f where f of x is equal to f of p, then this quantity isn't really well defined at all, right? So there is something not quite right going on here, right? There's something technical at play, and it has to do with this possible function. So that's super disappointing, because otherwise this is a really elegant, really cool proof. And I should say, other than this possible issue, this proof is valid. This proof is really nice. So it does work outside of this technical issue. So that's too bad. We're all a little bummed out. How do we fix this, right? How can we salvage this? Well, the main idea is really solid, right? The idea of sort of taking this quantity, breaking it up across, two different fractions, one of which is going towards what we want it to, the other one is going towards, well, maybe I should say one of which is going towards this piece, one of which is going towards this piece. So that's a great idea. There is just some technical issue that we have to get around, and we're going to do it through the introduction of a real interesting function, right? In other words, we are going to try to get around this by introducing a function that is sort of piecewise defined specifically to get around this issue. So we are going to get around this by defining a function phi of z as follows, right? So phi of z is either defined using a difference quotient, g of z minus g of f of p over z minus f of p. And that's in the cases where z does not equal f of p, right? So for most of our z values, phi of z is defined like this. However, if z does equal f of p, then I define this explicitly as g prime of f of p. Yes, so we're going to define this, this new function to help us account for the flat function and to sort of get around that issue. Because in our flat function, let me just draw that. Oh, let me just draw that off to the side here. Oh, we'll get it right. Here we go. Right. For the flat function that we had on the previous page, right? Pretend that that's nice and flat right around C, right? Or right around P, I suppose. Then at this point here, this is f of P. And so at these points, I will define this phi function, right? Phi of f of P will not get a 0 divided by 0 error. Phi of f of P will get a g prime of f of P as its output. So in a sense, this sort of extra step that I'm doing here is plugging a hole in this difference quotient that was previously there on account of a 0 divided by 0 error if I was plugging in z equals f of P. So, and I should say this phi of z will loosely fulfill the role on the previous page that was happening over here. So it'll loosely sort of it'll fulfill the role of this piece, which was previously potentially problematic. Or I should say this piece down here that was previously potentially problematic. So a slightly technical definition of a brand new function phi, but we can make a note that phi is continuous at f of p, right? And to do that, let me see, to do that, use blue for this, boop. To do that, we can make a note that says the limit as z goes to f of p of phi of z, right? This is what it would mean for this function to be continuous. The limit as z goes to f of p of phi of z is really equal to the limit as z goes to f of p of g z minus g f p over z minus f of p, just plugging in for what phi is. But that, by definition, right, by definition of limits, I should say, is equal to g prime of f of p. By definition, I should say of derivatives, by the definition of the derivative, that's equal to g prime of f of p. And that is just equal to phi of f of p. So we were able to show that the limit as z goes to something, right? The limit as z goes to something of phi of z is equal to phi of that something, which is exactly what it means for our function phi to be continuous at z equals that something. So this is just by the definition of continuity from the beginning, or from chapter 6. From the definition of continuity, phi is continuous at f of p. So we know that this function is continuous. Furthermore, we can actually show that this holds true, right? So this equation holds true. And it's actually, I think, not too hard to show. We have to break it into two possible cases. Case one, right? So case one, if x equals p, sorry, I should say it this way, if x equals p, this just simplifies down to 0 equals 0. All right, so if x equals p, then g of f of x minus g of f of p, that just becomes g of f of p minus g of f of p, so that equals 0. This becomes something times 0. Right, so if x equals p, this equation just becomes 0 equals 0. If it does not equal p, so case 2, we can divide to get, divide to get, and now we're going to divide the f of x minus f of p to the other side. So we get g of f of x minus g of f of p over f of x minus f of p equals phi of f of x. Right? And that's true because that's how this weird phi function was defined to begin with. So if x does not equal p, then this would, or maybe I should actually say, I can divide this over to get this, which is exactly how we originally defined phi up here. Now I realize I probably actually misspoke in my case 1. I think we need if x equals p or if f of x equals f of p, right? Because that was the issue, or that was a potential issue, is what happens if I had an x value for which f of x was equal to f of p. They both had the same height. If we have this flat function over here. Well, if f of x equals f of p, I can't divide. This doesn't make sense. But I'm still in this case, and I still get g of f of x minus g of f of p, so that still becomes 0, and this still becomes 0 as well. So, okay, so this is helping us account for this potential flat issue. No matter what x value I'm looking at, maybe this quantity doesn't make as much sense, but this quantity right here, or this equation, does make sense and does hold true for all x values. So we are almost in a position to prove the chain rule here. We have that our function phi is continuous. We have that our function satisfies this equation for all x values. And now let's see if we can bring it home. So the observation that we can make is that we're still trying to compute. So we're trying to compute g of f prime of p. So that's still the limit as x goes to p of g of f of x minus g of f of p all over x minus p. Okay, that's still what we're trying to compute. That's just the definition of the derivative. But looking up here, I recognize that the numerator, the g of f of x minus g of f of p, can be rewritten as this thing right here. Right? So I will actually go ahead and rewrite this using the numerator. I'll actually try to save some space and jump down here. So this is the limit as x goes to p, and let's rewrite that numerator as phi of f of x times f of x minus f of p all over x minus p. So this is the sleight of hand that allows us, and slash the very technical sort of clever move that lets us sidestep the issue that was happening in that seductive, more straightforward, earlier false proof. Here, I'm jumping over and replacing this with that phi because I cleverly defined phi to allow this equation to hold true for all x values, even the ones at which f of x was equal to f of p. So even in this situation here. So what does that get us? So we can rewrite this now. This is the limit as x goes to p, phi of f of x. And now let's leave the phi by itself and let's jump and sort of condense the rest of that into f of x minus f of p over x minus p. Right, so I'm just shifting that, that denominator primarily to put it under the f of x minus f of p. So according to our limit laws, we can now break this up into the limit as x goes to p of phi of f of x times the limit as x goes to p of f of x minus f of p over x minus p, provided that both of those limits exist. And now we can do the same thing that we did in the previous false proof, but we can do it without potential incident. So just like before, this piece, the limit does exist, and this equals f prime of p. And for this first piece, well, we've introduced this new object. It's a little weird, but we know that the limit as x goes to p of phi of f of x is equal to phi of f of p because phi was continuous. And therefore, we're looking at the second case, which means that we are at g prime of f of p, which is exactly what we were hoping to be. So that should be a g prime of f of p. And then taking it all together, tying it all together with the grand flourish at the end, we get that the derivative of g of f is equal to g prime of f of p times f prime of p, which is exactly what we were hoping to show. Yay! All right, that is a fun but technical proof. And I always think it's really worthwhile to see the false proof first, because looking at the false proof and seeing why the false proof is false really helps sort of motivate where this weird machinery is coming from. So any questions, comments, concerns, thoughts at the moment?
So how did you know that you would make when z equals f of p? How did you know you'd make it g prime of f of p? Like, because you just jumped there. I don't really get how you got that.
Sorry, can you say that one more time? So you're looking right down here, you mean?
No, whenever you defined phi of z, and you set it into that piecewise function.
Oh, up here, you mean? Yeah. Like, why did I define the second line to be this?
Yeah, how did you know that it was going to be that whenever z was equal to f of p?
Ah, okay. No, that's a great question. So in short, maybe I should say, so I wanted to define phi primarily so that it equaled this difference quotient, right? So it could be whenever I plug in a z, this would be a difference quotient involving g's. So g of the thing I'm plugging in minus g of the point f of p over z minus, the point I'm plugging in minus f of p. And something that I know ahead of time, let me see, something that I know ahead of time is that my function g is continuous at f of p. And so because g is continuous at f of p, I know, sort of off to the side, / maybe on the previous couple slides, I know that the limit as z goes to f of p of that expression, g of z minus g of f of p over z minus f of p, right? I know that this exists, and by definition, this limit is some limit L, but we like to denote it as g prime of f of p. So g prime of, whatever I'm plugging in here. So this is true just by definition. That limit of that expression would equal this. So if I wanted to define my phi of z to look like this difference quotient, and I wanted to define phi of z in such a way that I could plug in f of p, because otherwise I'd get a 0 error in the denominator here, this is the natural sort of choice to plug in here. Or I should say, this is the natural way to define this weird phi. It's defined this way so that the limit of phi as I get close to f of p will actually equal the value at f of p. So maybe that's a super roundabout way of saying, Joe, that I knew that I could take this limit. That limit would give me this. And so since that's the limit of the function as I approach f of p, I can just sort of artificially define the function to equal that at f of p. It's sort of like filling in a removable discontinuity to make a function continuous. And I would fill it in specifically with this as the height value to make that function continuous.
Yeah, that makes sense. Thank you.
Cool. No problem. That's a great question. Because I do think in some ways it sort of feels like mystical that we've sort of summoned this this phi. So I just wanted to, thank you for asking. Happy to clarify. Any other questions?
Dr. Ross. This isn't as technical. This is just kind of a smaller thing. When we change, so for the function, when we make it a g of z function, I know that we're assuming that p and x are in the domain of A, right? So when we change it from z to f of p, aren't we changing that function, because we let f of x be z, so aren't we changing the domain from A to B?
Let me see. So the function of, so the function in the domain, you say when we're changing it sort of in
yes, right there, from
this
x
step down here. Okay.
Well, no, from, I guess, just where we go from x, the limit as x approaches p, to the limit as z approaches f of p, like more in the blue star area.
Mm-hmm. Okay. Yeah.
So because that originally was like the limit as x approaches p, like in our false proof where we multiplied by f of x, and
Yes,
you know what I mean?
I think I do. Let me speak to that and tell me if I'm off base. So if I go, man, you can't really see that because it's all covered. So I guess there is a question as I plug things in about whether I'm plugging in elements from my original domain A or plugging in elements from B. right? Because again, we had this set A. I'm going to write this in the far upper right, so maybe we can see that there. So I had this set A. We plugged elements of A into F. That gave us elements of B. And then we plugged those elements into G to get, you know, just our output. So that was how our composition was set up.
Mm-hmm.
So Z, right? When I take my Z values here, I'm imagining that my Z values are in B.
Okay.
So Z is an element of B here. Because I need to be able to evaluate G of Z. So yeah, so Z should be inside my set B. However, I don't think we ever, I don't think we ever violate that. If we sort of look through here, I think the weirdest line possibly is sort of this equation right here.
Mm.
And for this equation, I'm plugging into phi. I'm plugging in f of x. So x was some element that I could plug into f. So x is like an a value, an element of a. So f of x is an element of b, and I'm just plugging in an element of b into my function phi. So in here, there's an element of b. In here and in here, I'm plugging in elements of b. And yeah, so I think we're okay in this line, and sort of similarly down here, let's be careful. I think I'm still thinking in every piece here, the Z values are all elements of B, depending on whether I'm plugging them into G or further down the line if I'm plugging them into phi. So I think it's okay. Is that, I guess, does that address the issue, or did I sort of miss the boat there?
No, yeah, that makes sense. Thank you.
Okay, cool, cool. Okay, cool. Any other questions? So we're just about out of time. I think maybe to, you know, to outro a little bit on the chain rule. This is a proof. Every time I sort of revisit it in real analysis class, I have to sort of pause and sit back and sort of stumble through it to make sure that I fully understand it. Because it does feel, at least to me personally, I feel like there's something sort of weird happening here. And it feels in some sense slightly unmotivated or challenging, sort of where this phi came from. So this is always one that I love to revisit to try to better understand. I think going through the false proof and trying to make sure you understand why the false proof doesn't quite work is really fun. And then seeing how defining this thing this way allows us to sidestep the false proof is really, I think, a really valuable endeavor. So going forward, what we're going to do next is we're going to pivot to the other big results involving derivatives. They're less about computing derivatives and more about applications of derivatives. So specifically here, I'm thinking about the extreme value theorem and then the mean value theorem. So I do think that Wednesday's class will be similar to today's class in that we'll probably have a whole group discussion about these sort of big results and how we can prove these results using this sort of structure that we've been spending the semester building up. So that is all I've got for today. I am happy to stick around to answer any questions. I'll also be pivoting to Discord here in a little bit. So I'd be happy to meet you there. Otherwise, have an absolutely wonderful rest of your day. It was so good to see you all. And yeah, if I don't see you, I will see you on Friday. So take care, everybody.